In this video, I'm going to derive the complex exponential definition. Now, there are a few different ways I could have chosen to do this, but I have chosen to do this via this differential equation. So this is a complex differential equation, but it is actually quite simple to solve, despite it being complex, because we can use just A-level maths methods to solve it. The only thing that's going on here is we've got an I, which is the square root of -1, which we wouldn't actually see this kind of differential equation on even the A-level further maths course. But it is a differential equation. We've got a derivative, dz by d theta, and then on the right-hand side, we've got a constant times z. So it's a completely valid differential equation. And what we're going to do is we're going to separate the variables. So bring the z over to this side. I'm going to get 1 over z dz, and that's going to be integrated. And then I've got the I is left on this side, and that's going to be integrated with respect to theta. Okay, so that's my separation of the variables. The left-hand side then is going to become the natural log of mod z, using A-level maths methods, and the right-hand side is going to become I theta. But all the integration symbols are now gone, so I should add c. Get rid of my logs. I'm going to get z is equal to e to the I theta plus c, or as we would usually write it, ae to the I theta, where a is equal to e to the c. Okay, so that is the solution of this differential equation that we get by separating the variables, and that is a correct solution. That is the general solution to this differential equation. Okay. However, there is another solution to this differential equation, and it looks like this. This is my claim. I'm going to claim that this function of z also satisfies the same differential equation. So just to remind you, the differential equation was dz by d theta is equal to I times z. So what I'm going to do is I'm going to take this definition of z and differentiate it. And I'm going to take this definition of z and times it by I and show that those two are equivalent. So z is going to equal, I times z is going to equal I times the cosine of theta plus I squared times the sine of theta. But by definition, I squared is -1. So that's going to be I times the cosine of theta minus the sine of theta. So that's I times z. Okay, the other side was dz by d theta. So dz by d theta. Cosine is going to differentiate to negative sine. I, yes, is complex, but it is just a number. It's just a constant. So it behaves like any other constant. So it's just going to sit there. And then the sine is going to differentiate to the cosine. And we can see that these two expressions are the same. I cos theta minus sine theta, and minus sine theta plus I cos theta. These are the same. And because they're the same, then that concludes that z equals cos of theta plus I times sine of theta also satisfies the differential equation. Okay. So we've now got two expressions of theta which satisfy the differential equation here. But there can only be one solution, or at least up to one arbitrary constant, because it's a first order differential equation. That is the only solution. So we can conclude from that these two functions must be somehow related. So we can conclude that ae to the I theta must be in some way identical to cos theta plus I sine theta, which is a true statement, and we need to find the value of a for which this is true for. Now, we don't really know how to take a complex number and exponentiate it at this stage. So the only number we can really plug into this is theta equals 0. So that's what we're going to do. If we plug in theta equals 0, then the left-hand side is just going to be ae to the 0, which is a. The right-hand side, we get 1 plus 0. So that tells us that a is 1. And that concludes that e to the I theta is identical to the cosine of theta plus I times the sine of theta. And this is the basis of all the complex number theory that we are going to be working with over these coming videos. Okay, this is the kind of the new idea of complex numbers in second year further mathematics. Okay, it's a very powerful tool relating exponentials to trigonometrics. And we use this for a variety of different reasons to get various results. Okay. All right, so that's one you need to know. You need to learn that, and that allows us then to exponentiate complex numbers because we can plug in any value of theta into there, and that will give us our answers. Okay. And before we wrap up this video, there is one special case I would like to consider, and that is when theta equals pi. So now we've got this relationship, which is a true relationship, and we'll be able to see that a bit more clearly when we do Maclaurin series as well. But when theta does pi, then we end up with e to the I pi on the left-hand side, and that is equal to cos of pi plus I times sine of pi. But sine of pi is 0 and cos of pi is minus 1. So we get e to the I pi equals minus 1, or if you like, e to the I pi plus 1 equals 0. And that, it's just a factual statement. It's like the statement 1 plus 1 equals 2, 1 plus 1 equals 2. It's just a statement of truth in mathematics. This is also just a statement of truth. It's not an equation. There's no unknowns in here. Everything is known. But it is very famous in mathematics, quite often described as Euler's identity, because it encapsulates so many fundamental things within the subject of mathematics. So, for example, we've got addition. We've got multiplication, and we've got exponentiation. So that's three basic operations that we apply and use in mathematics. It's also got some constants that we use. So e and pi, these are two very famous irrational mathematical constants which are used throughout mathematics in a wide variety of different applications, and that they're just appearing here together, which is lovely. And then we've got this new constant that we've been introduced to in the last year, I, where that one is very fundamental to a lot of mathematics as well, as we delve into the complex numbers. And then it's got 1, which is the multiplicative identity, and 0, which is the additive identity. So these 5 fundamental numbers, these 3 fundamental operations of mathematics, all wrapped up into one neat little bundle. Mathematicians just often describe that as a very beautiful identity. But past that, it's of no use. It's just a statement, just like that is. That this is one that's useful, that actually has use, because theta is a variable. All right, that concludes this video. We're going to be delving into this a lot more in complex numbers. So exciting stuff. Stay tuned.